Our second video where we continue writing this tactic, rewrite LE, which rewrites an inequality. Suppose the goal is of the form A is less than or equal to B and H is a hypothesis of the form C is less than or equal to D, and all of these are natural numbers. Then if either or both ends match, then things get rewritten using transitivity of nat.le. So let's see. Last time what we saw in the previous video is that we can match things, and we defined this match function. This is what we will use. So we use this at meta m level. A couple of things to clarify about last time, but term I said tactic m sits is just a state monad. It's not actually. There's a stack of state monads where each level has an additional state, and tactic m is higher. So anything at meta can be used in tactics without further command. Also, if you were alert, you would have noticed that actually all my tactics were wrong, in the sense that I forgot to say with main context do, and since these were just to illustrate, it's okay, but let's do them. Okay. So that said, now let's get to this did not affect the correctness. So what we want is something which will where I can uncomment these examples. That is, I have three natural numbers and I want to show x is less than or equal to z. By transitivity, I can rewrite either, and that will give me the other one left. Or if I actually have one of the hypotheses x less than or equal to y, it just closes it. Okay, so let's start writing the tactic. It's a bit complex, of course. So let's start. So what we have is elab rewrite LE. That's what I'm calling the tactic. Okay, and it does take a parameter, which is a term. Okay, so t colon term, where t colon term, and this is a tactic to, well, this one we are actually using, so let's not forget with main context do. Okay, and let's start the body of the work. Let H, let's catch the hypothesis, is elab term, and T and none. Okay, so we have got our hypothesis. Okay, and we have to match two things. So we match slash both H, match inequality, match LE of H, and match LE of get main target. So there are cases. So where this is sum of AB and some CD to, for the present, let's just say sorry, and dash to, again sorry. We'll deal with the second sorry, which is easier first. Okay, just to clarify, what has happened here is I've matched the match LE of H. That is, H has, oh, I'm sorry, this was wrong, of course. What I want to match LE of the infer type of H. Okay, so let me call it H type, infer type. So I took the hypothesis, I inferred its type, and I'm trying to see if both get main target and H type match. So let's be verbose here. Let me just say let target is get main target. So I have the main target and I have the less than or equal to type, and I just want to check whether they both match of target. So if both of them are inequalities, then we have to work further. Otherwise, we just throw an error. Throw error. Did not get inequalities. You could try more informative errors if you were actually writing a production tactic, which will help the user debug, but these are for illustrations. Okay. So now what about these two? When we want A, B, and so A and B, C are expressions, B and D are expressions. I want to check whether they're equal or not. Okay. Now they may not be literally equal as expressions. What we want to see is whether they're definitely equal. That first equal slash L, is definitionally equal. A and B, and let second equal is definitionally equal B. Sorry, I want to no, I want to check if A and C are equal and whether B and D are equal. Okay, so these are the two checks we want to make. Well, what if they're both equal? So now let's run through our cases. Okay, so first of all, if first equal to and second equals, then we are in good shape. Okay, so they just close main goal. And well, I have to give it a name, rewrite LE and H. Okay. So this is a valid tactic, and but however it works only in our third case, okay, which is when the first equality and the second equality both match. We can even test it. Indeed, it worked in this case. Okay, so rewrite LEH closed it because the tactics matched. But in the first two cases, if one of them matches, then we are not done. Uh, then nothing happens. They simply fail. So let's deal with when the case where only the first one matches. Okay. So suppose the first one matches. So let me just say else if first EQ, then let me just say sorry, else we'll fill these in. If second EQ, then sorry, and if none of the equalities work, throw error. So I can say else, throw error, neither ends matched. Okay. Let's simplify things a little bit by using early returns. So if first equality, then we are going to return. Okay, so it's all right. We can do it either way. So neither ends matched. This is a case where we will have these things. Okay, so what happens in the case of first equality? So then A, the hypothesis is of the form AB, the goal is of the form CD, and A is C. So now your new goal should be, we have already proved that A is less than or equal to B. So what remains to be proved is B is less than or equal to D. And then we can use transitivity. Okay, so we will, so let me just record that. So have A equals C. So H is C is less than or equal to B. And we need to show the new inequality we need to show is B is less than or equal to D. Okay. So what we have to do is we have to change the goal. We have to create a goal for B is less than or equal to D. And then we have to prove our original goal in terms of H and that new goal. Okay. So to create a new goal, we have to create a new unknown, which is our old friend a meta variable. So, so let new goal, we'll make a fresh expression mvar. Okay, and I'm going to just say sorry for the moment. Fresh expression mvar, some capitalization error. Okay, so we want a new goal, and this is supposed to be the type of the new goal. So let's call it new target. Okay, now we have our old friend, and here it really makes a difference. We're going to make app an m. Okay, so nat.le. Oh, okay, here is not so bad. It will be really big when we use the other case. So we need B is less than or equal to D, so I just copy BD. Okay, we'll make new target. Okay, and now we're going to have a new proof. Of course, the proof will involve the new goal as the inequality. So let's call it proof. And the proof is going to be a proof by transitivity. Nat.le transitivity of the result. Sorry. What we want to prove is by transitivity, we want to prove the result, which was our original goal. And our original goal was C is less than or equal to D. And so what we have to use H first, because H said that A, which is, so H is C is less than or equal to B. So we use H first, and then we use the inequality B is less than or equal to D. Okay, so we have, which is our new goal. Okay, so we have got pretty far. So what we have done is where the left hand sides match, we constructed a proof. Now the proof is going to have type, which is the original goal. Okay, but the proof will be in terms of a new goal as well as the hypothesis. So now we can assign a new goal. So what we do is let goal, I'm being deliberately verbose here again, is get main goal. Just to show you what kind of creature is this. The get main goal is a meta variable. What we can do is assign to it a value. This is saying that I solved the equation for you, but I actually I actually solved the equation introducing a new variable. So this is not a full solution. Okay, that's fine. But here we have not closed the main goal. So goals remain. We can't simply close the goal. New goal is now the goal. So we have to replace main goal by the goals that have been created. And in this case, there's just been one new goal. I believe it's a list, not an array, because the goals are ordered. Now new goal is an expression. We don't want an expression. We want a meta variable ID. So we just get it out of it, which is here. Okay, so this is the expression that we have. Okay, so now let's just test this. This is supposed to be, so we'll just return if the second equation happens. So we have to see what, so that will give a low level error. So is this a case where the first one matches? Indeed, we are in good shape here. So what happened is when we rewrite LE, we ended up with the goal y is LEZ. It's written in this form because this is, if you see, nat.le yz. Okay, so that's what it got written to, not the less than or not the le.le that you might have expected, which is what we usually get inside lean. So this showed us our tactic in operation. What we did is we have a equals c, so we have h is cb. What we did is we created a new goal. We gave a proof of our old goal in terms of the new goal, assigned the proof, so this solved it. But then we were careful enough not to claim the problem is fully solved. It is solved modulo new goals that we have created. Okay. So now we are again extremely parallel situation here. Let's just check what we have here. So in this case we have, let me make the comment, have in this case the second equality but not the first equality. So we have b equals d. Okay, so I should put these in code to read them a little better. So b equals d. So we have b equals d. So h is now the other way around. So h was the equality that a is less than or equal to b, and so b equals d. So h is a is less than or equal to d. And we need now that c is less than or equal to a. Okay, just to check this quickly again. So our goal was c is less than or equal to d. Now b turns out to be d. So what we know is that a is less than or equal to d. So if c is less than or equal to a, we are done by transitivity. Okay, so we need this. Let's just copy and correct all these things. There will be many changes. Okay. So first of all, our new target is not b is less than or equal to d. It's c is less than or equal to a, and we make this into our new target. And crucially, when we are using LE transitivity, we will have C is less than or equal to A first, and then A is less than or equal to D as the proof of C is less than or equal to D. So our new goal comes first in the transitivity, and H comes second in this case. Okay. Now we can have these. Let's test this out and then make a few comments. Okay. Ah, well, oh, I'm sorry. Why were there no goals to be solved? Am I going to get a low level error? Okay, so we are going to try and debug this proof. Suppose I remove this, am I going to get a low level error? Indeed, I got a low level error. That means I did not assign these numbers correctly, so it's a good exercise in working out what went wrong, okay, with the copy paste. Indeed, the goal turns out to be a silly copy paste error. This happens with copy paste all the time. We completely forgot to replace the main goal. Okay, so there were no goals to be solved earlier because we assigned a proof to the goal, so they thought the goal was done, and there were no new goals created. So when lean reached this stage, it saw the goals, but it checked whether any meta variables in the goals were unassigned, found they were assigned, and thought they were done. Okay. So indeed we are done here. We have handled all the cases which happen. We did not check the error cases. You can check them as well, and with some more examples. A few comments. Here we really did make append because nat.letrans, if you hover on it, you see it has implicit parameters nmk. So of course we can figure out those nmk. There are a, b, c, d, and with two of them coinciding, but it's a pain. So instead we can let lean fill in the implicit parameters. Okay. There is a even better method which will let you choose which implicit parameters that you have to fill, but this is the most convenient where it works. So, and another thing that I have not highlighted so far, though it's very basic, is this double tick. I mean double back tick that I use with names. Double back tick with a name means it's a global name. So if you had for example an open nat and then you just said le, it would resolve to nat.le if it can do so correctly. So this makes things correct, but the other very important benefit is that it prevents typos. Okay. If you expect a name to be globally defined, better use double backticks even if you are giving the fully qualified name. Okay. So with this we have seen a range of tactics, and we will continue to build upon this series of videos, but we have seen already a few aspects of metaprogramming.